My name is Emily McBride. I'm the president of the NASA Space Grant Robotics Group from Arizona State University. And this is our ROV named Gauss.
Who's Gauss?
It's the mathematician. It's actually not an acronym. It's just the name. So we have a 3-year-old team. This is our 3rd year competing in underwater robots, and we kind of formed the team in order to do a few main goals. One is to provide us students with hands-on experience. We learn a lot in our classrooms, but we don't actually learn how to apply these kind of things. So this gives us an opportunity to learn and apply the knowledge we have. In mechanical classes, you learn how to use SolidWorks, but you never learn how to machine. So we kind of take what we learn and extend it out into actual applications that we could use. Also, so we could learn about the different kinds of engineering out there. Systems engineering. Right now, most of us are engineers and scientists, but we all have our specific concentration of electrical, programming, mechanical, aero, bio. And here we get to see how all the different engineering blends together into one big systems. And we have mechanical people wiring up the robot to get better knowledge, and we have all the subsystems and engineering bleeding together. And also to spread the message of math and science and engineering. And we do this by outreaching to the community, kind of being a large figure on campus as roboticists and giving people a chance to see how cool science and engineering can actually be. And we do that by building robots at competitions such as this. The frame of our robot, as you can see, is fairly modular. It's a box, it's a square. And we did this so it's easy to mount to, easy to create. We designed it with simplicity in mind, easy to mount things to. Daisy, good morning.
Okay, so the way we kind of built this frame was, it was actually designed around this giant box in the middle. We just built everything else around it. And you can see there's slots here so we can move things back and forth with ease. And there's these mountings here that weren't necessary at first, but we had some trouble with some of the the camera housings. So they're here to keep the housings from moving. And you can notice how these are slotted out in the corners, and that's just to allow extra visibility for the cameras.
Yeah, this was something that we designed in SolidWorks first. You can see our SolidWorks design taught us how to use SolidWorks, and then we took it all to the machine shop and actually built it. So it was a great evolution of how we build things. Okay.
All right, so then our main electrical housing right here is this big box that our robot was designed around. From past experiences from different members, we found that gaskets and just in general square boxes, people didn't have very good luck keeping watertight. So we went the big round 8-inch cylinder right here. Because it's round, there's no pressure points. It's even pressure all the way around, allowing the O-ring to be compressed evenly. And then we have one O-ring. We played around with doing multiple, but we found that really one was enough. And then we did a little math to figure out the O-ring dimensions, like how thick that groove needs to be. And we found that approximately 120% of the width and 90% of the depth of the O-ring made like a really perfect groove. And then we tested this down at what was it, Lake Pleasant. Dig it down 40 feet. It was all good. And actually, before we actually machined this, we had it water jetted for the connectors, those holes. And then we're using Volgate connectors for those. They're commercially available, right?
Yeah, so we have a disconnectable tether. And all of our parts, we could reuse our different components more readily because it's not directly wired and glued into a box.
For the electronics, we have on board, we have batteries 12 volts and 6.6 volts. Batteries that are 12 volts are lithium polymer. The 6.6 volts are lithium iron phosphate. The reason that we went with the two different voltages is because we initially designed it with power converters on board, but due to weight and size, and that also allowed us to reduce the size of our tether. In it, we have 5 speed controllers. The speed controllers run brushless DC motors, which we have custom made this year. It allowed us a lot more thrust. The speed controllers run off of, they say between 5 volts and 15 volts. I believe it's 15 volts. And And so we ended up going with the 6.6 battery, the volt battery, so we didn't have to reduce them with voltage regulators because they're less efficient. We do have some voltage regulators in the robot to power the microcontroller and things like that. We also have LEDs on board. Those are going to be powered by a buck converter. The buck converter basically takes the voltage that we're sending it and converts it to a lower voltage and allows us to have more current, so we can power our LEDs with that.
The control system is based in 3 parts. One of them is the Arduino side, which is what controls the actual robot, pulls the sensors, sends how much thrust force we send to the motors, which motors to turn off, which motors to run, things like that. The second part is the back end, which controls how the Arduino communicates to the actual computer and how we control the actual robot, which is using an Xbox 360 controller. We do this, we can actually connect any type of controller. It doesn't have to be an Xbox 360. It could be a generic store-bought one or even PlayStation. And then the third part is the front-end GUI design, which displays all the sensor data. It's based on like the Raptor view, if you see in the picture. We also have compasses, so we know where to go, timers. We also have designed an Xbox picture, so people can see what button they press, other people as well. And all this, most of the program is all done in Java, except for the Arduino side, which is done with Arduino code, which is the C++ variant.
Sensors. On board, we have a Razer IMU. It's 3 accels, 3 gyros. This gives us better control for pretty much when we're using the manipulators, so that we can steady the robot if we're trying to drag something or lift something that would normally change our buoyancy that's preset for the robot. We have external sensors on this robot. We have a compass with a 1/2 degree resolution, like Scott was mentioning earlier, and Daniel as well. The temperature sensor and a pressure sensor as well. So our cameras this year, last year, the past actually 2 years, we found that you'll put cameras on a robot and go and test, and then you'll go in competition and you bump something, and the arm will be 2 degrees out of the view of the camera. So we're like, all right, we're gonna fix this year. So we have we actually have 3 pan-tilt camera systems. There's only 1 housing sitting on the robot right now, but we have 3 total and 1 fixed camera. They're done with 2 micro servos and the 4 or 3 inch diameter tubes. I think they're 3.
3.5.
3.5 inch diameter polycarbonate tubes.
Here we have the manipulator, so if you want to move things around. The first one that we have is carabiner clock here. It's on this side. This is for the missions that we can grab onto the broken ROV that's already in the pool. It's actually one of the simplest sensors manipulators we've made. It's just powered by this motor, and the spring actually pulls it back, so we just have to turn the motor on, and it locks itself. Very convenient. We have the box clock, which is on this end, and then we also have a secondary bot that's not here, the keys.
Yeah, we designed the